There we go. Let me start all that over again. um, Actually, I'll just quickly refresh what I did. Thank you for noticing that. So first, we've created a function called showMyTarget, and what it's going to do is draw a picture for us. That's its only purpose in life. And that picture is going to be in a 10 by 10 region, so the aspect ratio is 1:1, and it's going to draw 8 circles centered at okay, you're all going to get muted again. There we go. Centered at center X, center Y, in progressively increasing diameters. Then it's also going to plot the strings lists MYX and MYY as little red circles. MYX and MYY can take on the lengths that are needed. They can have one thing in them, or 100 or 10,000. And then we use the add artist method in the Matplotlib to add these circles and then finally render the plot. So that's all this function does. And then we were talking about accuracy. And so the concept of accuracy is a measure of how close to the true or population value is our estimate, or how close we are to the bullseye if we're shooting at a target. Supposing we're estimating the mean value, then the bullseye, what we're trying to hit, is the population mean mu. Our estimate is the sample mean x bar. And now I want to consider a graphical simulation below. And this is related to, but somewhat separate from mu's and x bars. We have a target that we think is centered at 0, 0. We're going to take 10 shots at the target and evaluate our performance. So let's say we're kind of old and shaky like me. And sometimes we hit the bullseye and sometimes we don't, but over 40 years of shooting, on average, we tend to get good scores and tend to hit near the center. So that would, this is our model. Our model has 2 parameters, mu, which is where we tend to hit relative to the bullseye. So think of it as a distance from the bullseye. And sigma, which is how shaky we are when we let the shot go. And we did some simulations with just 10 shots. So like it says here, after 40 years of shooting, we're pretty good at getting near the center, but let's say we're not perfect. So we do that, and there's our shots, and that would be a pretty good score. Actually, that'd be a 99. That'd be a really good score. And we have a histogram of our performance from the center of the bullseye. Now, the reason we get a high score is by design, shooting games, they have to give you some area to hit for the scoring. Let's then think we do a lifetime of shooting. Let's really do a lifetime of shooting. And we've pretty much obliterated the center of the target. So there's the shock and awe approach to target shooting. But let's look at our histogram. Our mean distance from the bullseye is 0.75. And now that's just a number. Depending on the size of these concentric rings, that might be a more than adequate performance or not. So let's continue with the example. Again, the target, we think it's at 0, 0. We're going to take 10 shots. But let's say we're kind of sloppy. We sometimes get good shots and sometimes get bad shots. And our, in addition to being kind of sloppy, we're also a little shaky. We'll do 11. We'll do 10 shots. And that's not a very good performance. If we look at our mean value, we're 5 units away. So let's get smart. We'll just add a value of 5 to our hit tendency. So we dial some 20 minutes So we'll dial some changes in our instrument and we'll take the 10 shots again. And that's better. And so those distances we're adding, what we're correcting for is offset or a bias. And that's actually a good analogy for the meaning of the term bias. See, what was our average? Our average distance is 1.5, so let's subtract that from 1, which will be minus 0.5. And just like in real marksmanship, every time you make an adjustment, something else changes. And so now we've had a pretty substantial impact on our ability to hit the center or our accuracy. And we'll go ahead and take a lifetime of shots and see how good we are. Done. We still obliterated the target, but if we look at these two pictures, ask yourself which one is the better marksman, 1 or 2? 1 or 2? So I'm seeing 1 in the chat box. That's correct. That's my intent for this simulation. Let's look at the two histograms. Shape-wise, they look almost the same, but mean distance from the bullseye for number 2 is almost 1. So in terms of histogram behavior, number 1 is the better marksman. So that was accuracy, how close we can hit a target. Now we have the added bonus feature in regression that we don't know where the target is. What we have is a sample which gives us some guidance on how to aim. Our next important concept is precision. So accuracy in this particular graphical analogy was conferred by our choice of mu. Precision is the measure of the ability to repeat things. So the concept of precision is a measure of the repeatability of estimates. In this context, in our case, the dispersion is the metric. In other words, the variance. So if we consider our graphical simulator below, I have a cat tail in my face. The target hasn't moved. We're going to take 10 shots and evaluate our performance. So let's say that we're really sloppy in terms of where we tend to hit, but we're very steady when we release our shots. So our sloppiness or our accuracy set to -4. In this case, our steadiness is 0.3. We do that, and I did 10,000 shots, and we've obliterated a hole right here, which is good because we get to reuse the target. So in this case, we would be able to visually quantify, well, that's a pretty steady shooter. Just the aim is off. And so if we could adjust the aim a bit, rerun the simulation, and indeed we're getting close to the center. One more time, and we will have obliterated it. And in this case, our mean distance from the bullseye is 0.376. Now what's interesting here is we've set our measure of accuracy to 0, which is what it should be. That's where the target actually is. And we still have a mean distance from the bullseye for our 10,000 shots. And what that introduces is a very important concept that you'll see in later classes. There's variation that's introduced irrespective of how good our estimate is. And so that variance is in some cases irreducible, but let's say we get even steadier. We redo it, and we pretty much have clobbered the bullseye right there. We still have non-zero mean distance. There's always some variability, at least if this is a probabilistic representation of reality. And there's a technique you're going to learn in your statistics class called analysis of variance. It actually can be done with our regression packages. It's kind of built in. It's a added bonus feature of regression. Farang mentioned it two laboratories ago. and showed you how to interpret some of the outputs on that. And in the analysis of variance, we can attribute the variance. Let me go ahead and rerun this simulation at a different value. It's possible to attribute the total variance, the portion that has to do with the variability, like we are demonstrating here, and the portion that has to do with our guess of how accurate our shooting is. So here we've adjusted our accuracy and our variance. So we're going to actually just start from this example. So that would be in competitive marksmanship, that would be a really good target of 10,000 shots. You basically would be a god of the shooting world, which is not a very big sporting world, but there's probably 1 million people around the world that do this and get sponsorships. That would be really good performance. Real people can't do that consistently. Dude, you really got to get out of the way. Oh, this crazy gato. So this bias is a term that's given to, you'll see it in other classes, called systematic error or offset. It's similar to the concept of distance that we've been using in our examples, the distance from the bullseye. Again, using the marksmanship analogy, if we have a precise rifle, precision meaning either the sigma or the mu. Anybody, which one? When I say precision, which of those two metrics am I referring to? After you're going to go ahead and remotely control a gun to shoot for you, you're still going to go to jail for the rest of your life, Rame. Which of the two, when I say the word precision, which of the two metrics? Good, thank you, Andrew. I'm talking about sigma, how steady we are when the shot trips. So if we have a precise rifle that shoots a known distance from the bullseye, such as in this picture, that's still a useful tool because we can either adjust our aiming point. So here, instead of aiming at the black dot, if we aimed up here, this obliteration of the black dot should occur there, or we adjust the sights, and that's actually the whole point of sight adjustment. We either adjust our aiming point or the device to account for the bias. So bias is not a bad thing. Biased estimators are also not bad things, although they tend to be discounted in the world of statistics. Whether it's preferred is unbiased estimators, because in the world of statistics, the target actually moves around. So bias is not necessarily a bad thing, but we want to find estimators that are unbiased. So an unbiased estimator, for example, our sample mean is an unbiased estimator of a population mean. The offsets are not attributable to random behavior. They're attributable to being wrong. So that's what an unbiased estimator gives you. But a biased estimator, if it's all you have, is useful. And in instrumentation, for instance, so where I was gone most of last weekend was working on some remote instrumentation. So I have these sensors that are provided to me by a manufacturer. And the manufacturer says like 212 counts of the Hall detector is equal to 20 liters. That's not right. That is their average linearity count for their sensor, but the prudent engineer has to check each one. So each of the sensors was run through 5 experiments where we measured the actual water that went through it and the number of counts that was returned by the sensor, and then we use that to create the correct multiplication factor. And it turns out the manufacturer supplied one is close, but it was not close enough to be used with all the different sensors. So that's a bias correction. Because in theory, each count of the Hall detector should correspond to a precise volume of water that passed through the instrument. But in real life, while that's engineered to be so and manufactured to be so, there's variations we can't account for. The temperature can change. The instrument could have been calibrated at sea level. We're operating at 3,200 feet, which in the whole scheme of water compressibility isn't very much, but it might be enough to drop a count and so forth. So that bias is corrected by determining the offsets, and then from that point forward, we just use the offsets or the bias correction. Our next concept is something called residuals. In the context of this target shooting example, I created a residual, which is the distance from the target. It's not exactly true, but it's close enough for discussion. And it's the distance from the target that our model, the rifle, places the estimate or shot. First we do an example with biased and unsteady hands. That's this picture, so -4 and 0.3. And we see that the mean distance from the bullseye is 5.66. And if we use that information to correct, let's bring it to 0, and now our oh, that was 1,000,000. That's going to take a while. Yeah, we really obliterated that sucker. So now the mean distance for the bullseye is 0.37, and now I'm keeping track of the dispersion. So this is how spread out that red cloud is. And we're going to need that idea coming up shortly. So a way in this particular analogy of determining the spread of that red cloud is if we know how far away this target plane is from the launch point, we actually can create an angular deflection, or how wide that red blob is in terms of angles. And they're very small angles, so minutes of arc. So a minute of arc at 100 meters corresponds to about 3 centimeters deviation. So we can do the deviation vertical and horizontal, and we know what angle is there. And so if we're a good marksman and we're shooting for people's lives, not taking lives, but to preserve them, if we're known to be able to make our shots within 1 minute of arc, that's saying that with high confidence, we know that the red dot will fall somewhere 3 centimeters to the left, or 3 centimeters to the right, 3 centimeters above, 3 centimeters below, in a 3 centimeter circle around the point of aim. We have an analogous concept in our linear regression modeling called interval estimates of either the parameters or the predictions. And again, Farhang showed you that last meeting, because I remember actually paying attention to that part. And we represent those in our graphical representation with those dashed lines for confidence intervals. And a confidence intervals either of the prediction or of the regression line. We also can have confidence intervals on the individual parameters. So those interval estimates play the same role in regression that the angular deviations play in obliterating black dots with red dots. And so that's my dispersion. And it would take some more programming to actually convert this into real numbers to figure out from a picture how accurate or inaccurate you are. But let's just go a little bit further. So with perfect aim, our average distance is about 0.37. Wait, that's amazing. It did that twice. Let me rerun that. I wouldn't expect the numbers. Oh, it's 1,000,000. That's why. Yeah, I guess with 1,000,000 things, our statistics is probably in pretty good shape. Did I just crash the server? Come on, come on, come on. We're waiting. Probably shouldn't be taking 1,000,000 shots. But in the military industrial complex, that's how you make a profit. So. We may not regain control. I can proceed forward and wait for the response. I found it odd that I got the same average distance and the same dispersion, but with 1,000,000 darts being thrown around, that doesn't surprise me a bit. So we're now going to improve our situation a little bit, and we're going to put our target rifle into a mechanical vise. And let's pretend that what that does is changes the steadiness from 0.3 all the way down to 0.01. And when we do that, we'll get the 1,000,000 red holes right here. So we get a dramatic increase in the apparent performance. Now, all we've done is changed our variability. Our accuracy hasn't changed a bit, but by reducing the variability, our precision has increased dramatically. And when we look at our histogram, our mean distance has gone down by a factor of 30, and our dispersion is 6 parts in 10,000. And when you get to statistics class, you're going to learn a technique called analysis of variance, which is a practical application of these ideas. In your statistics class, you won't be messing with bullseyes and red dots obliterating black circles, although that's kind of fun. And nobody was harmed in the making of this program. The distances in this particular example are always positive. So if you were to look at that distribution, anybody recall what distribution we've studied earlier in this semester that has kind of that same appearance?
Gamma distribution.
Very good. I'm impressed. Thank you. Yeah, it's gamma distribution because we are constrained to just the positive number axis. That's very bad number theory. Sorry. But very good. I really didn't expect anybody to guess it right off the bat. I'm kind of stunned now. So let's go ahead and just look at a single, yes, Braid, you also had it. Let's look at a single example where we're going to take into account the most important part that makes the statistics of this somewhat difficult is our friend, the moving target. Everybody loves moving targets. So now we're going to go back to a person that has adjusted their point of aim to value minus 2.5, so it should hit 2.5 left, 2.5 low on average, and they're pretty steady. But now we've moved the center of the target to a different location. So this is like real life because we don't actually know where the target is. And we're not going to take that many shots because I don't want to. Oh, I still have a clobbered computer. Let me kill the kernel. It's not going to let me regain control. So I'm not actually run anything. So pretend I just ran this. This is the picture we get. So now our red obliteration spot is here, but the target has moved to minus 1, 3. In our particular simulation model, we actually can't chase the target very good because we don't have the ability to do left, right, up, down the way I built the model. But we do have the ability to look at the mean distance from the bullseye and our dispersion from the point of aim. And so in our statistical model world, we have a target that we can't see and we don't know where it is. So our best we can do is to take a sample and make inferences on our sample. And so that concludes my analogy of target shooting and statistics in regression. And if I can regain control of my server, note to self, do not do a million simulations of stuff. Fortunately, I think I have a local copy. So this is no longer on the server. This is on my computer. This is our friend, the Conda. What kind of Conda? Anaconda. I want to move to the next. So I'm a little confused in Anaconda, as maybe you are, because it looks different now. So let's now depart from the fun game of obliterating black dots with red targets. Let me run the entire thing. As soon as this renders, we will. Oh, this still has the million. Yeah, when you do a million, do it on your local machine. Okay, so let's look at a multiple least squares regression case, which is kind of a departure from shooting at targets, but it will allow me to introduce some of the terms that we see in our regression estimators. Let's suppose we want to measure, or we want to relate the abrasion resistance of rubber to the amount of silica filler, X1, and the amount of hardener, X2. So we add silica fibers to rubber to increase its strength and abrasion resistance, and then the hardener chemically bonds the filler to the rubber polymer chains and increases the efficiency of the filler. So all that information is just background. It was invented by the problem writer to help confuse students and grown-ups so that we would mistakenly focus on the apparent chemical engineering and not focus on the rather limited data set that we're provided. And we have data from a particular experiment. So Y represents some metric of abrasion resistance. I don't know what units it's in, it doesn't really matter, but it looks like it ranges in values from the low 80s to around 100. And then X1 has values ranging from minus 1.5 up to 1.5. X2, another predictor variable, is ranging from minus 1.5 also to 1.5. And then there are clear relationships. We'll actually do some plotting. And let's examine some different models. The two I want to examine are 2 and 3, which should be 1 and 2. Why does it do that? There we go. Our models 1 and 2. Actually, I guess we could do some other models. We could just do a single. Well, we'll look at that in a second. First model is a simple one where we're going to find a coefficient that we're going to multiply on the silica fiber metric variable, and a coefficient that we're going to multiply on the hardener variable, and then intercept, and then we're going to predict the value of Y. The second one, we're going to look at x1, x2, x1 squared, x2 squared, and then x1, x2 as predictors. So this one is, these are both multilinear least squares, or multi-variable. But this last one is actually reusing variables in the squared and the cross term. So we'll look at that, and then we're actually going to get to look at some pretty cool plotting. So first, our experimental data. So at this point, there's nothing magic there, but let's introduce some terms. And I was working on my make-a-bear function. I think I finally, XY model. Cool. We need make-a-bear. Where did make-a-bear come from? Well, see, I save everything I do, so I don't have to rethink stuff every time. So now I have the make-a-bear model, build-a-bear workshop. Good. And what I want to do, I want to put in, let's see, XY, X1 comma Y, and I don't really have, I guess if I do the model on, yeah, I'll just do, this is not really how I intend to run make-a-bear. So what I'm going to do is I'm going to plot X1 versus Y. So this is just looking at the data. And I want to cut all that out. I'm going to lose my cool 3D plot, but I'm going to save it down here. All right, so before we look at these models, remember that first thing we mentioned early on is the exploratory data analysis. So let's look at graphs to see what there is to see. So I'm going to plot X1 versus Y, and I'm going to repeat it. So this is going to put a dashed line in the same place where we have the dots, because I haven't modeled anything yet. Oh, that's horrible. Let me just go ahead and suppress that right now. There we go. So there's our picture of X1 versus Y. So do you see any pattern there? When our value of X1 is kind of small, our Y values are less than 90. When our value of X1 is big, two of our Y values are bigger than 95, but one of them's not. And when we're at the pivot point here, X1 equals 0, we have a abrasion resistance in the 95 to 100 range. So anyone just looking at it, speculate a correlation coefficient?
0.001.
Okay, good enough. Yeah, there's not much correlation evidenced in this picture. Let's look at the other variable, X2. We do it again. That has a little bit more correlation appearance, at least to me, but it has our famous, if we were to look at a hole that contains everything, we'd have a line down here. We have another one up here. It has that horn shape, homeo, a hetero, skedastic. I didn't just say a dirty word. That was a question. Homo or heteroskedastic from that picture. So we got a couple of heteros. You are correct. The variance is changing with respect to our position in X. So individually, neither of them is terribly informative. Let me turn make-a-bear off, go back to the build-a-bear shop. Let's just plot this stuff in a cool 3D plot, which other than being cool actually doesn't help very much. So here's a three-dimensional rendering. So on this axis is the X1, the silica. On this axis is the X2, the hardener. And on the vertical axis is the abrasion resistance. You can see there's some clipping here, and I'd have to fuss with this to get the rendering to be better, but I actually wonder if that has anything. I think that's a 111. Let's see what happens if we make that a 2. This is how to do real Pythoning. That's a bad move. Don't make that a 2. There's a way to make the image area bigger, probably in the plot figure call right here. I could probably do the same thing. Yeah, right here. Let's try this. We're going to teach some real programming today. Let's see what that does. 50-50 chance. Either it'll work or it'll be a disaster. There we go. There's probably other things we could change the rotation. So here we see our prediction plane down here on the bottom. And we'll see if we're in this corner, we get some different y values as compared to this corner. So there's vague evidence that there's a relationship between x1, x2, and the abrasion resistance. So what we want to do is, as it's presented right here, I would say if a prediction somewhere in here is nearly impossible. When we're doing regression, what we're really doing is we're passing geometric objects through those data points. So the first one we're going to pass is a plane, P-L-A-N-E, not a 737, but a 737 MAX. So we're going to try to draw a plane in that picture that passes through all those points, and each point is as close to the plane as we can get it. And the equation of the plane we're going to use is this one, y equals x1 times some coefficient plus x2 times its coefficient plus beta 0, which plays the role of intercept. And because I'm a lazy person, I went and used stats model to extract the ordinary least squares fitting tool. And actually, I'm surprised I didn't leave the reference to it. Oh well. And so in this one, we're going to create a variable, an object named x. We're going to add a column of ones to it. We're going to build it into a matrix, capital X, and then we're going to apply ordinary least squares. So just like Farang showed you a couple of lessons ago, boom, we're done. Now let's look at the output, because now the output is more than just gobbledygook numbers. It's mostly that still. We pass this plane through it. Our R squared is 0.6. Adjusted R squared is probably a better metric. 0.5. So the plane does appear to have a positive linear correlation coefficient relative to the underlying data. Our F statistic should be a 5. That's weird. That's coming up 7. The computer must be right, not me. The probability of our F statistic is about 1%. So there is, again, evidence that this model has some predictive value. But let's more importantly look at these numbers. These are the upper and lower interval estimates for the associated variable. One nice thing to know about the ordinary least squares in the stats model is it completely screws up the ordering of your vectors. So x, that's the daily spam call. There you go. So the x2 in this table actually corresponds to, oh, I got this backwards. Let me get this. So one of the reasons you're supposed to read the instructions with the various packages is the packages do some, did I just rerun that? Yeah. Do some interesting things is they order stuff backwards. But that's not a big deal once you first notice it. So this is telling us that on our x1 variable in the package, which corresponds to our list named x2, that's really confusing, I understand that. The coefficient has a 95% confidence interval of lying between the value of 2.2 and 12.4. The p-value associated with the coefficient at rejection is about 1%. So that is a statistically significant coefficient, and any other thing we do, it's worth keeping. Our x2, which corresponds to our list name x1, similarly ranges a value from minus 1.054 to 9.054, but it has a pretty high rejection probability, 10%, and so we could probably ignore x2 because it's not adding much improvement. And then our constant is ranging between 89 and 98 with 95% confidence. And then there's a few other statistics here. So what I perceive from this is that there is some predictive value in x1 and some predictive value in the constant. Let's just test that conjecture because that's really easy to do. x1 is x2. So I've got to make sure I keep track of things correctly. If I rerun it, I think I retained the wrong one. Classic. So my adjusted R squared is 0.443, and that's if I retain my list named x2. When I go ahead and put my list name x1, so I add another variable, rerun the least squares, I don't really gain that much in my adjusted R squared. Most of my behavior is explained by that variable and that variable. Now in this particular instance, I would probably retain the useless variable because these are pretty crappy models as it is anyway. Let's go see what it looks like in our cool three-dimensional plotting routine. So what I'm going to do is I'm going to construct a design matrix, which is a fancy way. I'm going to come up with values of x1 and x2. I'm going to just create a grid, and then I want to plot what that grid looks like and see what information I can see when I make the plot. So hopefully I've just created the grid, and I'm going to use a really cool thing that comes out of the statistics package, which is the model is already stored in an object named results. I'm going to use the predict method. I'm going to supply my new design matrix, and I'm going to get a new set of estimates, and I'm going to plot those. So I've done that. I do that, and it didn't. Why didn't it make my plot go? Oh, I'm doing local makeup errors, aren't I? Yeah, there we go. So let me get the size up so we can see it. Where is it? Hopefully everybody's getting nauseous as I move back and forth. Hit run. And this is the plane. So I haven't figured out how to render the actual points on the same picture. That would be really handy. It would be really cool if I could shade that in. That's for y'all that are looking for extra credit because you want to do silly stuff like that. Don't waste your time on it. We'll save that for some other time. So this is the rendering of the plane that best goes through these markers. And now we have a predictive tool. So if I have a value of silica of minus 0.5 and hardener of plus 0.5, I would go up to where it intersects the plane, and that gives me the example of abrasion resistance. And doing that graphically is nearly impossible. So one of the messages here is that the rendering of 3D is just to help you visualize. It's not a very useful tool for as a methodology, but it's really useful tool to look at what the output looks like. Let's go ahead and add the x1 squared list, the x2 squared list, and the cross term list, x1, x2. So where do those come from? We were smart enough to remember to make them up here. And now all we're going to do is change the input to the API. Literally change that line of code and then rebuild the fitting matrix. Same methodology, hit run, pray, good, it worked. And now we have the variables x1 through x5, and let me make sure, and it's ordering them. So x1 in the fit corresponds to that list. x2 in the fit is that list, x3, x4, x5. I don't think that's a flaw of the package. I think that's a flaw of the Dr. Cleveland when he built his design matrix. I think I built it the wrong direction. It works, it's correct, but you have to keep track of that in your own brain. So let's look at our adjusted R squared. So adding those two variables gives us the illusion that we have a better fit. We would have to apply some various other statistical tests to convince ourselves of that illusion. But there was some value in the R squared world of adding two more variables. Let's look at the rejection probabilities, or basically the measures of significance. The constant is significant. We're going to need to keep the constant. The p-value rejection on variable x4 is 0.3%. 0.3%. So that one is significant. X2 is 2.8%. That's probably worth keeping. X1 is 5.2%. We might want to chunk that. X3 is useless. And X5 is 3.2%. The constant essentially is returning a value of 0. So the constant is absolutely vital. And now let's look at our confidence interval. So our 95% confidence interval on X1 is between 0 and 10. 95% confidence interval on X2 is -8 and 0. Our 95% confidence interval on X3 is -4 to +3. So it has no idea where that one is. Our X4 confidence interval is 3 to 10. Our X5 confidence interval is 5 to 7. And our constant is between 92 and 103. So interpreted pretty much in the same fashion as before. Interestingly enough, the probability of rejection of our F statistic hasn't changed much. That's kind of cool. And we can now go ahead and let's render it and take a look at what this is going to look like. Except we want to make it big. Where did I do the rendering? And what we're seeing is when we complicated our linear model, we actually changed what we were trying to pass through the data. Instead of just being a plane, we have a parabolic shape in the x2 y-axis, another parabolic shape in the x1 y-axis, and when you put them together, it's called a hyperbolic paraboloid. So we have a very peculiar curve function that we're trying to pass through it, and this curve function is yet another model. Our next step would be to apply statistical goodness of fit test, which Farang has shown you in previous lessons, to make the decision of whether the model that has 5 estimating or 5 prediction features outperforms the model with 2 prediction features in a probabilistic sense. For what it's worth, if we applied a proper F test to both these, we would conclude that the higher order model doesn't confer much benefit in prediction. But keep in mind, we're only going with 11 things. And that's about all I have for today. So I've everything you've seen here has been shamelessly stolen either from this this tutorial or this tutorial. So this one was pretty cool, fairly hard to translate into something simple enough for my little feeble brain to understand, and our friend Geeks for Geeks. And they have a full example there, and it wouldn't take a genius to go look at the scripts I presented in these scripts and see that they look an awful lot alike. This is where I got the 3D plot scripting from. And then this stuff down here is for me. It's just left me behind. So let's actually take a couple minutes and discuss this idea of the development script. So as you're making your own notebooks, each of us will come up with a different way of doing it. I don't actually know how Farang does it, but how I do it is when I copy and paste stuff, because I haven't found a convenient way to highlight a whole section and comment it out, which in RStudio is really easy because you just comment the source. I've got to imagine it's here somewhere in edit. But I don't see anything that remotely corresponds to commenting. So I keep separate blocks of stuff that I've been stealing from various places. You'll also notice that I, at least in this one, adhered to keeping track of where I got the script from. And if you were to take this URL, you would not find this script exactly. I've modified what was there for my needs, because it certainly isn't going to use the same labels I have. And there's a whole bunch of other junk here that it had that was unnecessary. And by keeping these code fragments around, it makes it fairly easy as we're doing development to grab a chunk, put it into your active cell, run it, diagnose failure, fix it, and then keep moving. And then the other piece of guidance, we're close enough to the end of the semester. You're working on projects now, I hope. Go ahead and give stuff stupid names that you can remember. So I will never forget Make a Bear as my plotting package. And so that's why I'm using things like that. And come back up here to show my target. Same thing. Go ahead and take liberties with the scripting language to give your things names that are either easy to remember or are descriptive of what that thing does. So nobody who's been listening to this who hasn't passed out from boredom yet is going to forget that show my target is something that draws a picture of a target. So that's about all I have. Someone's in the waiting room, I think. There's a bunch of people in the waiting room. I make some critical comment like, an hour and 14 minutes is a little bit late, but maybe they got disconnected, so I will take that back. So Andrew Mara says he's really bad at statistics, but good at writing code. Yeah, we're all good at writing code. As long as we can copy and paste, code writing's easy. It's making it do what you want without having to go do a true development from scratch, because we haven't shown you how to do that. Let's see some stuff about grade books, value error, shapes. Good, I have no idea what they're talking about. Just adding D's here, one-dimensional 2D. Okay, cool. And yes, I think this is the first time we've shown a 3D rendering, Farang. So that's pretty cool. And
that was pretty cool.
And have you done them much before?
Not in Python. In R, I have worked on some copulas and joint probabilities and 3D plots, but never in Python. That was very cool.
Yeah, this, for what it's worth, it took quite a while to reduce the source example to the 9 lines of code that actually do stuff.
Mm-hmm.
And just a warning to everybody, you may get an error with this marker equals M activated. So the solution to that error when it comes up is this. You just take it out. And that's a consequence of how the Anaconda handles, I'm pretty sure it's in the MPL toolkits part, how Anaconda handles it and how the server version handles it. So I'm going to go ahead and give Farang control and try to
Thank
get
you.
the server back to life.
So we are going to begin the lab at 9:20. So if you want to take a break, you can. Dr. Cleveland, there are some questions about the winner and winners of the costume contest.
I haven't posted them yet, but we know who they are.
So that was the answer for that question.
Fiona won the celebrity guest designation, and then the other ones I can't remember. So Fiona already knows she's a winner, or whatever her real name is. And I'll get those posted eventually.
I think she was Kendall Dusk, I believe.
All right. Well, I always remember her as the green gal now. So let me go ahead and give you host.
Thank you. And they said that they cannot see the link for the labs, so I'm not sure if you haven't put it on Blackboard now. So about the exam 2, I believe you all can see your grades on the gradebook. The bonus questions on the take-home part are for the take-home part. They are not going to be added to your in-class section. I also saw something about the lyrics project. I received 2 other emails over the week. The lyrics project will probably not be available for this semester. So far at the moment that we're speaking, you have 2 projects to choose from. One of them is the concrete project, and the other one is the instrument calibration project.
Wait, so why is the lyrics project not available?
Yes, that will probably not be available for this semester.
Wait, why?
There are many reasons to that. The first one is that the formatting of it is not fit for our class.
Okay.
So quick question in the chat box. When it says use MENGR, MSE, and R2, do we those for all 3 models? You do that for all 3 models, and then you compare the results, and based on those values, you will be able to describe and compare the models better. Any other questions for me? I'm here to answer. Otherwise, just make sure that you have downloaded the dataset and the notebook for Lab 21. There isn't a lab link.
They're going to have a hard time doing that. Let me put it in the chat box.
I can do that as well if that's hard for you.
That's not a big deal if I can actually find it. GitLab 21. The server.
Dr. Cleveland, would it be okay if I remove the waiting room and allow everyone in?
Yeah. I don't understand how an hour and a half in they're having to reconnect, but it's life. The computers are just computers. Oh, I just said that out loud too on recording. Huh. Okay, there's lesson Lab 21 ice cream cone, right? There we go.
Yes. So the Lab 21 underlined class notebook file and the ice cream cone CSV file are the ones that you will need for today's lab.
Okay, let's see if I can fix this stupid server. I've stopped my screen sharing, right? Yeah.
Yes.
Amazon Web Services.
Maria, I just removed the waiting room, so if that happens again, you can easily join back to the meeting. And Brayden, yes, ice cream, and even better, ice cream cone. So it's 9:21. I'm going to start the lab. Do you have any problems downloading the files and opening the notebook? So it's all good. Okay. So after a week of talking about linear regression, some of you may have thought that that was it, but I'm here to tell you that you are wrong. We're going to talk more about linear regression today. So last week, we talked about linear regression. And I'm going to ask some of you for a very basic, simple questions, and I'm looking for your participation. So what is linear regression? What do we mean when we say linear regression?
Line of best fit.
Okay, good enough. Any other ideas?
The general trend of the data.
Okay, thank you. The answer that I have written here is that it is a basic predictive analytics technique that uses historical data or samples to predict an output variable, which is our target, or y. So what is our goal? What are we looking for? What purpose does it serve?
To try to use the historical data that we have to predict future data.
Yes, so prediction is one part. Is it the only purpose that it serves? Model population. Yes, you're trying to estimate things or information about your population. Model visualization. You can say that, but that's not really the purpose of linear regression. So if I wanted to tell you that there are two main goals, one of them is predicting and prediction. The other one is exploring the relationship between a bunch of inputs or predictors and a certain output. Thank you, Dr. Cleveland. So the server is working for those of you who were interested. Now, how did we make linear regression work? How did we build a linear regression model?
Didn't we use like an equation or a series of equations to model a best fit, or to like make a slope for us instead of having to like guess?
You're getting very close. It's kind of sloppy, but you're getting very close. So what was the equation that we built everything upon?
I kind of forgot what it was called, but it's like the mx plus b or whatever.
Yes,
yeah.
yes,
Good.
yes. The mx plus b or the beta x plus alpha. The name of those coefficients can differ, but that is the general format of a lines equation or a linear equation. Very good. And then I'm seeing some names in the chat box like OLS and MAE. What are those? What was OLS?
Ordinary least squares.
Yes, and what was MAE? First of all, MAE was mean absolute error. That was a goodness of fit measure and has nothing to do with the part that we are covering right now. OLS was ordinary least squares, and then MLE was maximum likelihood estimation. So these are two methods that we use to get what?
The slope
And
and the y-intercept.
yes, so we use those two methods to get an estimate on the slope and the intercept of that linear equation. Okay? And then once we got those, what could we do with them?
Plug them into the line of best fit equation.
Yes, and as I'm also saying in the chat box, to make the line, and once I had that line, what was that line? What did I call it?
The population or
No,
line of best
that
fit.
line is not, yes,
Yeah.
yes.
Right.
And Braden also said that in chat box. That was the line of best fit. And then we could use that line to basically do predictions or to estimate values of our target variable. Once we did all those, and that is when Brandon should come in and shine, how did we assess our fits?
With MAE.
Yes, and
Other methods like just get us a fit, MRSE.
thank you very much. These things that you are naming, RMSE, MAE, what were they? They all
fits metrics.
Thank you very much. Goodness of fit metrics or GOF metrics, and these are numbers that we can use to quantify the fit. We used another kind of analysis on our fits to assess their quality. What was that?
What was the question again?
So we used these metrics like MAE, RMSE, and that was one way of looking at a fit. There was another way, another method of assessment.
I'm just gonna say visual assessment.
Yes,
Okay.
thank you. Yes, visual assessment. And we use that to get an idea of how close our points are to the line of best fit and whether there is a difference in variability, whether there are certain regions that our model is doing better than the others, and that was visual assessment. So, do we have a question? Cool. We just did a review of whatever we did on last Tuesday and Thursday. Now I have a new question for you. How confident are you with a prediction that your model makes? If so far from what you've learned, if you find your best fit and you look at it or you use the metrics, can you tell me how confident you are with your values? It depends on how close to zero it is. It depends on how close what is to zero.
So like if MAE or RMSE is close to zero, then it's a better fit.
Okay,
Like
so
the lower value for the GOF metric, the better line.
good point. Good point. Let's say that I had a bunch of samples. I found my line of best fit, and I ran RMSE, and I got an RMSE of 0.01. How confident are you in this answer? What do you mean by who knows? Of course you are not, Rame, you're not a cat. Or at least I hope so. So Ileana, you want to elaborate?
I just meant, who knows? Like, have we done, I don't know if we would be able to give a percentage from what we know.
just take our word for it. Okay, not this time, but yes, Eliana, you were getting kind of close. Generally, when you are doing a prediction, you are making an estimate based on a simplified version of a relationship that exists between your predictors and your output. So in all of the examples that we worked on, we had a bunch of samples. We had one target variable. We know that in real world, in nature, there is a relationship between those predictors and that target. Do we know what that relationship is exactly? Correlation is one way for you to realize if there is some sort of similar direction between these two. But do we know what is the exact relationship between predictor A, predictor B, predictor C, and target? No, we don't. If we knew that, there was no point in doing all this, because if you know the relationship and you have the predictor values, you could easily and with 100% accuracy say what will happen. We don't know that. And that's why predictive models come in. Linear regression as a predictive model helps us to capture that relationship to some level. We are getting a simplified version of the true relationship. And I say simplified, not just because it is a linear representation. I'm saying simplified because we're making some assumptions to simplify the problem for our model. The overall fundamental idea behind modeling is that we are trying to simplify one phenomena in nature in a way that we can better understand it and better describe it. So we have created a simplified version of the true relationship, and we got an accuracy of 99%. That is the accuracy of your model. That is a different concept from how confident you are in that model. We will get to that more in today's lab. When we talk about errors in a model, what are we talking about exactly? Is it only one value with one source, or is it multiple values from multiple sources that we put together under one umbrella and we call them error, or the error of our models? Multiple, yes. So what are these multiple sources? Why do we end up with having errors in our model and Michael Caine crying?
It's
Randomness, variance. Come again?
Is it like each data point's error from our predicted model? So there's multiple data points, so that's why we have so many.
Correct. That's one way of saying that. Braden said randomness. What do you mean by randomness? Okay. Rami said variance. What do you mean by variance?
Well, like whenever we look at historical data, they're spread out. They don't conform to a line.
Exactly. And what does that tell you?
That we can't fully predict.
That, for example, using a linear model, you will not be able to fully capture the variance in your data points.
Yes.
Very good. So Braden also said there is more than one predictor. Yes, could be. There could be elements in those relationships that you are not even able to capture. You may not even know about them. Science has not made enough advancements for us to fully understand all the impacting factors. Generally, we say that our model's error comes from these three elements: the variance, the bias, and then the variance that is associated with our noise. The first two, the variance and bias, are things that have to do with our model, and we, to some level, can play with them and try to modify them. But the third one, the noise in our data, is something that is known as irreducible error. No matter what you do, there will be some noise. You can use many techniques in different parts of your analysis, starting from sample taking, to try to reduce that, but it will not be zero, not in real world. Okay, so up to this point, could you follow what I said? Do you have any questions about what I said? Okay, cool. Now we're gonna put a pin on this, and I have written a little story for you here. So let's assume that you were arrested by the King's Guard as you were minding your business in the streets of King's Landing for the crime of planning for the murder of King Joffrey Baratheon. As much as you hate King Joffrey, and I hope you do, you had no plans for killing him, but no one believes you. In the absence of witnesses or confession, you demand trial by combat because this guy made it look pretty cool in one of the best moments in TV history. But they inform you that the Germanic law to settle accusations is no longer used, and they are using another method. You get to choose a bowman. That bowman will make 3 shots for you, and if he hits the bullseye even once, you will get to walk free. Otherwise, they'll hang you. Did you get the rules of the game? Cool. So you have 2 options to choose from. The first one is Horus. Horus is known as one of the greatest target archers of all time. He's kind of old, and due to lack of an efficient social security system in Westeros, he has to work as a hired bowman for the High Court to earn a living. So that's how he has ended up as one of your options. You ask around, and you hear that he still can shoot a bullseye, but as his hands shake, he sometimes misses by a lot. The second archer is Daryl. He is also a well-known archer, but unfortunately he has a drinking problem, and I hope you know who I'm referring to. You have understood that there has been cases that he has shot the bullseye in all of his 3 shots, and then there has been cases that he has completely missed the bullseye. The thing about him is that his 3 shots are always very close together, or as Rami said during the lecture, he's pretty consistent with his shots. But sometimes it's the bullseye, sometimes it's not. So, based on these 2 options, who would you choose for your life? Horus or Daryl? So I'm getting Daryl because he's not shaky. I'm getting the old guy. He has a name, man. Pay some respect. I'd rather just die. Well, that's just giving up, Rame. At least give them a shot. Come on, give me your answers. I'm waiting.
The old guy, always the old guy.
Lee, no, you have to choose. You cannot shoot yourself. And
unlike Russian roulette, you can't choose not to play.
Yeah. By the way, thank you very much for those of you who saved me in the exam. That's why I'm here now. So I'm getting kind of a 50-50 feedback from you. Some of you are choosing Horus. So Horace is winning by a lot, but also Daryl has some people who want to bet on him.
So I think the reason Horace is better is because, like, assuming that Daryl misses the bullseye once, his precision is good, meaning all of his shots go in the same spot. So if he misses once, then the rest of his shots also don't hit the bullseye. But with Horace, he doesn't necessarily always hit in the same spot. So there's a higher chance, well, I guess kind of a higher chance of him hitting the bullseye.
I really liked your analysis. That kind of reminded me of that whole goat car problem. So you're saying that because Horace can shoot all over the place, there is a chance for him to get the bullseye, even if he misses the first one and even if he misses the second one. But with Daryl, it's basically if he gets it the first time, he will get it the rest of the cases. But if he misses the first time, he has missed your life.
Yep.
So the good thing about it is that you were just listening to Dr. Cleveland's lecture, and now you are knowledgeable enough on the content of precision, bias, and variance, and that is a good thing. So let us use the example and find out what Horace was doing and what Daryl was doing. We use the example above to give you an initial understanding of bias and variance and their impact on the model's performance. Given this is a complicated and yet important aspect of data modeling and machine learning, without getting into too much detail, we will discuss these concepts. So, in definition, in the formal definition, they say that bias reflects how close the functional form of the model can get to the true relationship between the predictors and the outcome. And variance refers to the amount by which the model would change if we estimated it using a different training data set. If you find that a little confusing and uncomfortable, you have every right to, because I don't really like that as well. But this figure is a pretty good one. So we have low bias, high bias, we have low variance, high variance, and then basically 4 different combinations. What is the ideal form?
The top left.
Which is?
The low bias and low variance.
Low bias, low variance. That is the ideal case. That is what we all want. But can we get that? Almost never. Very unlikely, yes. Almost never you get to have low bias and low variance at the same time. What is the worst case?
Honestly, I'd say high bias, low variance. Well, yeah, I mean, I don't know.
That was a good answer, though.
Either that or high variance, high bias.
Generally, high or high bias or high variance is something that we don't want. And again, something that we do not get. And I will tell you why in a moment. So I'm getting a question that what exactly is bias? I recommend that you definitely rewatch Dr. Cleveland's lecture on that. But for now, if I want to give you a very simple heads up, the bias can be interpreted as your error in estimating the mean of your population. And the variance can be interpreted as the error in estimating the spread or sigma of your distribution. But there are more to it, and you should definitely rewatch the lecture part to get a better idea. So now, looking at these 4, which one you think Horace was?
the high variance, low bias.
Thank you. Why do you think that?
Because he isn't precise, which is what bias is kind of, and then, but he is like accurate, so the high variance.
Okay. Which one do you think Daryl was?
High. I think it's high bias but low variance.
Why do you think that?
Because he hits in the same spot at the same time, but he's not likely to. But he's not likely to actually hit. He can hit anywhere on the target.
Exactly. So depending on how much he has had and what kind of drink he has had, he on a day he may just go out there and shoot all three right in the bullseye or completely out. But in all cases, he is precise, so his three shots are very close together. With Horace, the old guy, he has kind of a high spread, so he shots all over the place, and who knows, you may get the bullseye in one of them. So now, do you have a better idea of who you want to choose?
I'm sticking with Horace.
Horace. Come on, share your ideas. Vote.
I think Horace should get 1 million
All I'm
shots.
saying, hey, all I'm saying is he sober up my boy Daniel, and he's got it.
A lot of people have tried to do that. That's not going to work on him.
You can make him go cold turkey.
He has just killed so many zombies that he just doesn't care anymore. It's not impossible for Daryl to hit the target. No, it's not. If it was impossible for him, there was no dilemma. He has shot the bullseye in many cases with 3 shots, but also there has been cases that he hasn't shot it at all.
Take
Okay.
the bow and shoot
So
the king.
this-
Very good.
This whole dilemma is something that is known as the bias variance trade-off in modeling. We cannot have low bias, low variance. You get to choose whether you prefer your bias to be low or your variance to be low. And there is no silver bullet for that. It really depends on the kind of problem and the kind of relationship you are dealing with. Sometimes, in many cases, it really depends on the application. For example, if you are running an analysis on the relationship between blood pressure and a specific type of medicine that can help fix the heart's rate, this is not something that you can afford to be unprecise about. You need the highest precision that you can get. So that was just an example, and probably not a very realistic one. I just want you to realize that sometimes Daryl should be the choice, sometimes Horace should be the choice, because in real world, we cannot get low. Is there any questions? What do you mean, Braden? Why can't we have low? Yes, the reason for that, actually, I think I have already given you a link for that, but because this is an interesting topic, but it is way beyond the scope of this class. So I'm just gonna share these links with you in case you were interested in reading more about this. There you go. Okay. What is the SSN shortcut? Social security number? You want my social security number, man? So, any questions about what we've discussed so far? It's 10 to 10, so I've got to run a little. No questions? Thank you, Rami. Thank you, Braden. Okay, let's move on. We've talked about them, but I'm going to skim the text for you because some of you may be a little too lazy to read it yourself. Generally, in an ideal world, we want low bias and low variance, which we cannot have for reasons that you can read more about on the links that I sent you or just by simply Googling them. When there is a high bias error, it results in a very simplistic model that does not consider the variations very well. And in a case like that, we call it underfitting. We are saying that our model is suffering from underfitting. It is too simplistic that it can't really understand or capture the true relationship. On the other side, when the model has high variance, what happens is that not only your model is learning the relationship between the predictors and the target, but also it is learning the noise in your data. And when it learns the noise, it also means that it is not accurate. So from underfitting, from the case that your model is too simple to learn the true relationship, you go so high that your model basically is too complicated that it's not only learning the true relationship, but it also is learning the noise. And that is a bad thing, but quite on the opposite note, it is called overfitting. There are ways to identify those in machine learning that if you are interested in machine learning later, you will definitely learn. To summarize, a model with high bias error underfits data and make very simplistic assumptions about it. A model with high variance error overfits data and learns too much from it. And a good model is where both bias and variance error are balanced. The balance between the bias error and the variance error is the bias variance trade-off. You will learn more about that in those links. So the next question that you will probably have is, okay, I have created a model and I've got my fit. How can I measure the bias and variance of my model? Just as we had goodness of fit measures for accuracy and for errors like RMSE, MAE, Brandon's specialty, we have GOF metrics that can measure the bias and variance of a model. One of the most famous ones is the Nash-Sutcliffe model efficiency. And the other one is the KGE or Klein-Gupta efficiency. The Nash-Sutcliffe is basically in the ideal zone when it's close, when it's 1. So when the values are close to 1, you know that your model is doing pretty good in terms of bias. KGE or the Klein-Gupta efficiency was kind of built on Nash-Sutcliffe. And the good thing about it is that instead of giving you 1 number, it gives you 4 numbers. It gives you a number for correlation, the direction of the relationship, bias, and variability. And then the 4th number is the KGE, which is the 3 of them put together. So we are going to show you how you can do that in Python. Example 1, This is the example that we have worked on already, where we had a data set with TV spendings, radio spendings, and newspaper spendings and advertisement, and then the sales for a specific product. Now, let's say that we want to compare the performance of our linear models that use TV spendings and radio spendings as their predictors in terms of accuracy, bias, and variability. So the first part of it, I'm sure you feel comfortable with, but if you have any questions, just ask. The first thing that I do is that I read my data set. I define my 4 variables, and then I create my linear model with TV as predictor. And then I predict my sales based on that. Then I create my linear model with radio spendings as predictor, and then I predict my sales based on that. I'm using TV and RD to separate these 2 linear models. So at the end of this cell, I have created 2 linear models, and I have created 2 different sets of predictions based on them. Do you have any questions about what is happening in this block? And whenever I ask you this question, yes is a valid answer, no is a valid answer, maybe is a valid answer. Not saying anything is not a valid answer. Do you have any questions about this block of code? No, nothing. Thank you. See, you can learn. No, no, no. Okay. Keep them coming. Thank you, Hannah. Thank you, Jared. Thank you, Benjamin. I do. Okay, Max, go ahead and ask your question.
Okay, so for the second half of the code, where it says TV spending as predictor, that's just us getting the linear regression for that one, correct?
Yes.
And,
so basically, this is one linear regression model that is using TV to predict sales. This is another linear regression model that is using radio to predict sales. So I have 2 models, and I'm getting 2 sets of predictions based on them.
Okay, thank you.
You got it?
Yeah, that makes sense.
Cool. Any other questions? What exactly does it calculate? So, Braden, I am using the ordinary least squares method. So at this point, for the first line, the line that I'm trying to highlight, what it does is that it goes in and estimates the values for my slope and intercept based on the OLS method. Then it uses those parameters to fit the line. Then it uses the line to predict the sales. That's what's happening in the 3 steps. And then the exact same 3 steps for radio as predictor. You got that? Cool. Any other questions? Thank you, Sage. Okay. Now that we have 2 sets of predictions, we can go and get the goodness of fit measures. How can I get goodness of fit measures? What am I comparing here? Well, Rami, that is Brandon's specialty, but I will accept that from you. So when you say MAE, how are you calculating MAE? Are you comparing 2 things?
Like you're comparing what your historical data to your best fit line.
Thank you. So what is my historical data in this case?
The data that you get from the advertising.csv.
Yes, and which part of that do I care about at this point?
The sales.
The sales. So the actual numbers of sales and the numbers that I got from my TV model, that will be one set of comparison. And then I will again compare my actual sales with the predicted numbers I got from my radio model. That will be another comparison. Right? Cool. Now, first, let's calculate RMSE. And as you see, the first one will be between sales and TV pred. The second one will be between sales and RD pred. Sales is from my historical data, from the data set that I had, and these underlined pred ones are coming from my linear models. So the RMSE for my TV model was calculated to be 3.24, and the RMSE for my radio model was calculated to be 4.25. What does that tell you? Okay,
Tells us that
start
the
calling names. Go ahead.
So basically, the 3.2 is a better predictor for sales.
Which one is a better predictor?
TV ad spending.
TV ads. Okay, that's one way of looking at it. Do I have any other ideas?
How much of the data was varied? It's a way to, like, if the predictor was higher, it means that there are more data points away from the line.
Rame, looking at the first RMSE and the second RMSE, what can you tell me about the models?
The TV ad has the best fit line is not as affected by variance as it is in radio.
Which model is better?
TV.
TV is better because it has a lower RMSE, right?
Yes.
Okay. In the chat box, I'm getting that Audrey is saying TV is a better predictor. Max is saying that RMSE isn't. Lower RMSE values are better. And then Braden also got that. Rami got that. Okay, thank you. So I want you to realize something very important about GOFs. Whenever you're going to pass a judgment based on the value of a goodness of fit metric, make sure that you mention that in your final statement. So in a case like this, you will go ahead and you will say, based on RMSE, it seems that my TV predictor or my TV predictor-based linear regression model is doing a better job than my radio-based model. And you mention RMSE because you don't want to be deceiving people. You're only looking at RMSE, so that's what you will say. Is that clear? Cool. Now, the next one, we are going to look at R2. And again, we are comparing sales and TV pred, sales and RD pred. Running that, we are getting a value of 0.61 for TV and a value of 0.33 for radio. What does that tell you?
That the R2 predictor is better for radio ad spending.
Wait, isn't it closer to 1 that's better? So wouldn't it be the higher value R squared for that?
So Andrew, are you sure that R2 should be closer to 1 or should be closer to 0?
I thought it was closer to 1.
Google it.
Yeah, okay.
Google and confirm it.
Closer to 1.
Or you can
closer to 1.
You can Ileana it if you don't want to Google it, and you will get a rather reliable answer from her as well. So R2 is better if it's closer to 1. Based on what you are seeing between TV model and a radio model, what can you tell me?
The TV model is better.
The TV model is better. Is there anything else that you can tell me?
That radio is 31% accurate to the sales.
Mhm.
I don't know if it's the sales or the sales model, but yeah. And then same thing with TV, that it's 61% accurate.
Okay, so based on that, would you go on and say that your TV model is twice as accurate as your radio model?
Yeah.
Okay. Do we have anyone want to add anything to that or have an opposing idea to that? So first of all, the hint that I gave you on RMSE applies to all other GOFs, and I didn't hear any of you using that. So when you want to pass a judgment based on a goodness of fit measure, make sure that you put that in your statement. That's the first thing. The second thing, if you wanted to compare two models, do you think RMSE is a better measure or R2 is a better measure?
There's no such thing as a better measure.
Why?
They all they all measure. They're all interpretations of the data.
Cool. That was it? I thought you had more to add.
I don't know what else to.
It's all right. It's all right. Yes, we use different metrics to provide a more wholesome picture of our analysis and of our data. So now we are going to look at Pearson's R. You know what Pearson's R is, right? Yes, you do, Brayden.
You should remind Brayden.
So, do I have a volunteer who wants to tell me what Pearson's R and when you have seen it before?
Can we see Pearson in Lab 13?
That was a Pearson distribution. Very good that you still remember that, but this is Pearson's R and you have seen it more recently. And also for those of you who are into gaming, Pearson was the name of the cook on camp in Red Dead Redemption 2, but that was completely irrelevant. So, Kayleen, you're getting kind of close. Yes. So I'm going to count to 3, and if no one has given me the answer, I'm going to call out names. 1, 2, 3. Okay. Cody, are you there? Cody. No, you're not there? Oh, okay. So there was like 4 things to use, but Pearson was the most commonly used. So Cody, what would Pearson's R tell us? Do you remember when we used it? Why we used it? Cannot remember. Okay, it's all right. So Hannah, I know you're out there. Hannah. Oh, Hannah. That was from Toy Story. So tell me what you remember, Hannah. Oh, you cannot. Oh, okay. Max Rodriguez. Okay, maybe someone has helped you. Carson has helped you, and he has used Google. Pearson's correlation coefficient R is a measure of the strength of the association between two variables. Do you remember it now? Last week,
Isn't that basically just saying like that's just a goodness of fit measurement?
It can be used as a goodness of fit measurement, but last week we used that and we talked about whether two variables will go up together, will go down together, or have no relationship together. If I increase variable A, will variable B also increase? That was a high positive Pearson's R. If I increase variable A, will my variable B go down? That was a high negative Pearson's R. And then if I increase variable A, will variable B just remain constant and indifferent? That was a near zero Pearson's R. So I hope that you remember it now. Yeah, that kind of represents the slope. Pearson's R was for 2, and then another one of them was meant for more than 2. Cody, Pearson's R is for 2. Isn't it? Yes, it is between -1 and 100. So it's really amazing that you knew gamma distribution from lab 13 and you didn't know this from last week. I kind of take that personally to the heart. You remember Dr. Cleveland's lecture way better than you remember my talks. So, and he's not even looking at you. Okay, so we are going to use Pearson's R on our historic sales and our predicted sales. And for the first one, we get a value of 0.78. And for the second one, we get a value of 0.58. What does that tell you? That tells you the TV is better. Better how?
It has a stronger positive correlation.
Which means?
It's a better predictor
Of?
sales.
Okay, you got away with that. But the reason that I keep telling you that we need to use different GOF metrics is that because they give us ideas and assessments of different aspects of our model. Before I answer the question on R, I have another question for you. What is the difference between something like R2 and something like Pearson's R? What is the difference? The range. I'm not sure what you mean exactly, but I don't think that's the right answer. 1 var versus 2. No, both of them, we are looking at 2 variables. So when we're looking at MAE, RMSE, and R2, what were we measuring?
The goodness of fit.
That was a very general answer. The error. Brayden, what do you mean by error? What was error?
Was it like the distance between the historical data and the line?
Yes. So the 3 that I named, MAE, RMSE, R2, they care about the distance of your points to the line of best fit. R, Pearson's R, cares about the direction. So when you get a Pearson's R of 0.78, it means that in 78% of cases, the direction of your TV model is the same as to your actual observations. Exactly, Braden. So R and R2 are looking at two different things about your model. R2 looks at residuals, looks at errors, looks at the distance of your actual points from your line of best fit. R cares about whether your line of best fit is capturing the direction and the slope to the right degree. So looking at your TV model and your radio model, you can say that it seems that my TV model is a better predictor of the direction. Does that make sense?
Yeah.
Cool. So that is the main reason why we use different goodness of fit measures, because they give us different pieces of information. If they were just giving us the same thing over and over and over again, would be an indicator of our insanity to keep using multiple of them. We use different ones because they give us different pieces of information. Now, to calculate the Nash-Sutcliffe, what was Nash-Sutcliffe? Do you remember that? Oh God, Max. It's right there. It's part of today's lecture. Just listen to me. So Nash-Sutcliffe is a goodness of fit measure that gives you an idea about the ability of your model in getting a good bias. So yes, that is what I talked about like less than 15 minutes ago. So we are going to use the hydro eval function package, and notice that I'm calling that package in a new way. You haven't seen that. That is something I wanted to show you. Whenever you call the not just hydro eval package, any package, and you say import star, that will basically call all the functions in that external package. So in this case, I'm calling hydro eval, and I'm saying import star, and then I'm using the evaluator function from that package without having to call its name. If you may have a problem on running that on CoCalc. I'm not sure if CoCalc supports that, but if you're on your local computers, you need to go ahead and install that. That is an external package. So for now, just follow what I'm showing you. So the way that this evaluator function works, the syntax is that first you define the goodness of fit metric that you want. In this case, it's NSE, Nash-Sutcliffe efficiency. Then your predicted results, then your actual observed values. And I'm doing that once for TV, once for radio. And when I run it, I get these values. What can you tell me about TV and radio based on these results?
TV has a more positive trend.
This is not about trend. Something that you need to, I'm going to remind you of that, is that the perfect value for NSE is 1. So the closer to 1 you are, the better you are. But NSE gives you a sense about the bias of your model. So looking at these two NSE values, what can you tell me? Very good, Kaylin. That is a very good observation. That is not always the case. In this one, that's how it happened. But based on this, you can say that your TV-based model has a higher NSE value, which means that its performance does better in terms of bias and variance, because they're kind of connected. So both of them are biased. Basically, everything that you do will be biased to some level. What you want is to know which one is performing better than the other. This is a way to compare them. And since this one is closer to 1, this is performing better. So for KGE, it's exactly the same syntax, except that for NSE, we go with KGE prime. The reason that we do not go with KGE is that in 2009, there were one formulation suggested for KGE, and then it was modified in 2012, and KGE prime is the modified version. So when you run it, as I told you, it will give you 4 numbers. I tried to put them in the comments here for you. So the first value is the KGE, or the Klein-Gupta efficiency. That goes from -infinity to 1, and the closer to 1, the more accurate or the better the performance of your model. Then you get R, which is the Pearson product moment correlation coefficient. That is our famous R that we talked about. The ideal value is 1, of course. Then it gives you the value of gamma, which is the ratio between the coefficient of variation of the simulated values to the coefficient of variation of the observed one. So this gamma gives you a sense of how good your model is capturing the variance, and the ideal value is 1. Beta will be the ratio between the mean of the simulated values and the mean of the observed one. And of course, the ideal value is beta 1. So when you run it on your TV and your radio, you will get 4 numbers. The first one is the KGE score. The second one is your R, similar to what we have calculated earlier. And then your gamma and your beta. So based on the results of this KGE, both of your models are doing very good in terms of beta, but in terms of variance, it's your TV model that it's doing way better. So correlation and variance are the winners in your TV model. So overall, you can say that your TV prediction is way better than your radio prediction. So something to remember. First of all, the goodness of fit measures that we have covered so far are looking at different things. They're looking at different aspects of your model's performance. We look at several of them to get a better idea of how our model is doing. KGE, one of my personal favorites, is a very good metric because it gives you an idea about the direction, an idea about the variance, and an idea about the bias of your model's performance. And it also gives you a single score that reflects the 3 of them. So in many cases, in my research, where I had to, for example, write models that would predict the stream flow of a river, I use different kind of predictive models, but in nature, they are all regressions. They're kind of more complicated than linear regression, but they are regression. And KGE is a go-to because it gives you a pretty good idea about how your model is performing on multiple fronts. So I'm going to pause on this example because I have something more important to say, and then we will come back to this example to apply those. Do you have any questions about what happened in this example? About the way that we looked at these goodness of fit measures? And something to add, if you are having issues with this hydro eval package, you need to first make sure that you have it installed on your local machines. For CoCalc, as I said, I'm not sure that it has it. I actually would find it kind of unlikely because it is not a very common thing to have. And then for those of you who are using Jupyter, you can just go ahead and install it and then go it. It's nothing complicated.
So if you're using CoCalc, are you just kind of screwed?
Yeah. I would say so. Let me ask Dr. Cleveland at this point. Dr. Cleveland, for those of them who are only using CoCalc, would it be okay if they just skip the part that requires them to run NSE?
Yeah,
because if I'm not mistaken, later on the exercise,
the trick to using CoCalc was you would have to find where that module is and download the module and then upload it to CoCalc to install it, because CoCalc doesn't allow direct installs unless you pay them money, and then it just runs even slower.
So I have asked you to calculate NSE for your exercise. Maybe this is the time for all of you to go to your local machines and install Anaconda and have Jupyter running.
If you Google, it's the NSE Nash stuff. Is that Nash stuff?
Yes, yes.
There should be semi-primitive script that you could just drop in on your own to get that information. Yeah, the function Python. There you go. Who uses hands anymore? Yes. So that's a whole class right there. And
I think you can use it.
If you go up to the class definition, you have to define the actual class. Functions from, so there's the HTTP. If you scroll down, just touch right there. pydoc.net, that you'd have to be able to get that library. And then from there, you could just install it and run it. It seems like it's kind of complicated.
This is the package that I've just shown you. Yeah, I'm not sure if they can find that. Well, worst comes to worst, you can use one of these online NSE calculators and just give me the number in your notebooks. But I think strongly
would be the easiest.
Yeah, I strongly recommend that you move to
Anaconda.
Jupyter on your, yes, Anaconda and Jupyter on your local machines. Now, do not go and pay for CoCalc, at least not on our accounts. We don't want you to do that.
I think that's a waste of money.
Yeah. Okay, so moving on, we will talk about a term that you have heard before. Do you remember when we talked about confidence interval? Azael, about how to use or install Anaconda, there are videos out there. We have had workshops on it, and Dr. Cleveland had made recordings and he has uploaded them, so you can easily find them. So, do you remember when we talked about confidence interval? Don't make me call out names again, come on.
Yes.
Yes, okay. Rame, Ileana, whichever one of you feel more comfortable, just tell me what you remember about confidence intervals.
It's when we have like we have two cutoff points in the historical data, a high one and a low one, and using our margin of error, we can determine that, or what our confidence interval is. And basically, what we would say is, if, for example, we wanted a 95% confidence interval. We would have an interval where we have a 95% chance of having the value we're looking for.
Thank you very much. Thank you very much. So,
Brian, was it a single value or was it an entire list of values?
basically, the confidence interval will give you two values or a range that you expect the true parameter to fall in. So previously, when we talked about confidence interval, we were talking about hypothesis testing, we were talking about normal distributions, and we said, okay, if I have a sample and I get the mean of that sample, I can say that the true population's mean will fall somewhere around my sample's mean. My sample's mean plus some interval minus some interval, and this will be my range of possibilities. Okay?
All right.
So, with linear regression, we have a similar concept. We have a confidence interval, again, similar to what Brahmi said. It can be 95%, it can be 99%, it can be 90%. That number is not fixed. And we can say that once we find the line of the best fit, the true best fit of the population will fall somewhere around that. That somewhere is described by using confidence intervals. So I have given you the equations for that, even though I do not expect you to go out there and make calculations. Look at these plots, especially look at the one here. This basically means that there is a 95% probability that the true linear regression line, when we say true, we are talking about the population, will lie within the confidence interval of the regression line calculated from the sample data. So we had a bunch of sample points, for example, 1, 2, 3, 4, 5, 6, 7, 8 points here. We went through the things that we do, and we have covered many times at this point. And we get this line as the line of our best fit based on our samples. This is the y equals beta x plus alpha. These little dashed lines on both ends are basically saying that the true linear fit of the population will fall somewhere between these two lines around the line that we already have. So it may have a different slope, but it will be somewhere in between. That's the room that it has to wiggle, if I'm not mistaken with the English word. So by using these equations, you will get this line and this line, and you can say with a 95% confidence that your true population's best linear fit will fall somewhere in there. Do you have a question about this?
So basically, if we have any line in between those two dashed lines, it's valid. It's within our 95 percentile.
It is within your 95 percentile, yes. But when you say valid, I'm not sure what you mean by valid.
So like any of the lines like on the right side, since they fall in between, no, on the right graph.
Don't go for the right side yet.
Okay.
That will have me linked to the next part that I want to talk about. But generally, when you have a bunch of points, either through OLS or either through maximum likelihood estimation, you will get a linear equation, and that will be only this line, this bold line in between. When you get those intervals, you can say that, okay, within this space, I am 95% confident that I can capture the true linear fit. Does that make sense? Hello?
Yeah,
Yes.
That makes sense.
Okay, cool. Now, let us move on. In the graph on the left, figure 1, a linear regression line is calculated to fit the sample data points. The confidence interval consists of the space between the two curves, the dotted lines. Thus, there is a 95% probability that the true best fit line for the population lies within this confidence intervals. Now, we have another concept that it is called a prediction interval. And since we have already discussed this, if you look at this side, if you look at the right-hand side of these plots, these are possible lines. You do not get them. This is just an illustration of how we can draw straight lines between those spaces. So the line that you can get and we have achieved is this one on the left. You can look at the right side was it Brandon I was talking to? I'm not sure. As Brandon mentioned, you can assume that, okay, maybe my population best fit line is this one or is this one, but you can never be sure. That is part of the uncertainty. Does that make sense?
Yeah, it makes sense.
Okay, cool. Now we have another concept as along with confidence interval, and this one is called the prediction interval. Unlike the confidence interval, when we were talking about the entire best fit line, with prediction interval, we talk about each single point and not the entire line. So here we look at a specific value of x(x0) and find an interval around the predicted value y hat, such as there is a 95% probability that the real value of y corresponding to x0 is within this interval. This may not be the best explanation out there. So let me break it up to you. You find the equation of your linear best fit, and you have an x equal 2. You put x equal 2 into your linear equation, and you get y equals 5. Are you certain that it's the correct answer?
No, because we don't have 100% confidence level.
Exactly. So somewhere around 5, you can be up to a certain level of confidence that your true value will fall. So if the model has told you that y is equal 5, maybe y is somewhere between 4 and 6. Maybe y is somewhere between 3 and 8. Does that make sense? Brayden, yes, it's just a prediction, depending on the interval. Exactly. So we will take that concept and plot it in a different way. So here I have my examples on the x-axis and my output or y on the y-axis. So the model output in the example I told you are 5 is located here. But the observed value, the value that we had in our historic data, is falling here. So let's say it falls at 5.5. First question, what is this distance called? Error. Very good, thank you.
Ellipses.
So, come again?
Isn't it also called ellipses?
Mm,
The distance between an observed.
ellipses?
Is that not like the Greek letter used for like epsilon?
Can you spell that for me?
It looks
Yes,
like
no.
it's the first result.
This one? The omission from speech or writing. Epsilon, yes, yes, yes. In many cases, we show error with epsilon, yes. Okay, That was a relief. Okay, so we talked about this. We can calculate the prediction interval, and please realize that this is different from confidence interval. We can calculate the prediction interval and then move from our model output up and down and get this prediction band. So we can be, for example, 95% sure that the true value will fall somewhere between my upper prediction limit and lower prediction limit. Does that make sense?
And that's still with the 95% confidence, right?
That really depends on you. You can go with 90%, you can go with 99%. It really depends on you as the person who is running the analysis.
Right.
Cool. So when you are talking about specific points, it makes more sense to look at prediction interval. When you're talking about the entire line of best fit, it makes more sense to talk about confidence interval. That is the biggest difference. But know that these two concepts are quite different. Do you have any questions about confidence intervals and prediction intervals on a linear regression? If it falls outside, is it more likely to fall out of the bottom? In fact, when you are saying that my prediction interval is from A to B, you do not think that it is likely that the true value falls somewhere outside. You're talking about the inside only. Do I have any questions from confidence intervals, prediction intervals? Yes, no, maybe?
No.
Okay, cool, Rami. So now, this is another familiar example for you. This comes from your exam 2, and we also talked about it last week. Let's say that we have two sets of numbers, time, speed, and we want to explore the confidence and prediction intervals for our linear regression model. First, what I do is that I make a list of my time, make a list of my speed, I convert them to arrays, and I name them X and Y. X is my predictor, Y is my target. We already know the parameters for a linear estimation from what we did last week, but we are going to assume that we don't know that. So I'm running a linear regression based on OLS in a method that I'm not sure I have shown you before, so I just thought it might be nice for you to see another way of doing exactly the same thing. So this is one way of creating a linear regression. And once you do that, you can basically get the summary and get the parameters of that model, very similar to what we did before. So when you get the summary, you have seen this in a lecture when Dr. Cleveland does it. It gives you the coefficients, very similar to the values that we had. It gives you R squared, adjusted R squared, and some other information about your model that you may not necessarily need, but it's just good to have. So we created a linear regression model, and then I'm going to use this function WLS underline prediction underline STD to get my limits of the prediction interval. So by using this on my model, I can get my prediction intervals. And if I print the lower limit and the higher limit, I will get a bunch of numbers as expected. There is another function called the summary table that we can use. And by doing that, we can get our confidence intervals very easily. We just need to set up our alpha. Why I'm setting my alpha equal to 0.05 if I'm interested in 95% confidence intervals?
Because alpha is the difference between 100 and your confidence level.
Thank you very much for remembering that. Thank you, thank you, thank you. Alpha is our significance level. 1 minus significance level will give us the confidence level. So if I'm interested in 95% confidence, I'll go with an alpha of 0.05. Thank you very much. So I do these to get my prediction intervals, confidence intervals. And then if I plot this as is, it will give me this red line and these blue dots. Is there anything new in this plot for you? No, no, of course. But actually, I think I have to run this. So okay. Now, if I remove the hashtags of these two lines, I will get something like this. This is my prediction band. The one on top is my upper band. The one below is my lower band. So whatever you see, these green lines are my prediction bands. Do you notice that these two are also lines and not curves? Do you know why is that? Do you know why that's happening? Our model is linear, that is correct. But the reason is that for every single point that I have on this red line, I'm going up and I'm going down by the steps equal to my intervals. So if my initial line is a linear model, the one on top and the one below will be parallel to that and also linear. So that's one part of the things that I wanted you to get. So I'm putting these hashtags back and I'm removing these two. And what I get is these two orange dashed lines, and these are my confidence bands. So
wait, how did you get that?
I just removed these two hashtags for the orange lines. Yeah. So if you notice, this is not a line anymore. These two are curves because we are talking about the confidence intervals here. That is another way for you to differentiate the differences on a plot. So if you want to have everything on top, you will get something like this from your analysis. The blue dots are your historic data. The red line are your line of best fit from your linear regression model. The green ones are your prediction bands, and the orange lines are your confidence intervals. And that's all we talked about today. So I know I'm running out of time, so I've given you some references to go and read more about. Some of them I've already used to create this notebook. Some of them are just for more read, and there are some videos that you may find useful. For the exercise, we have given you a data set that is called ice cream cone, and it has recordings on daily temperature, relative humidity, cone strength, and cone weight based on noon readings for 20 days of cone making. And you're going to follow the steps and answer the following questions. In each part, you are asked to run different linear regression models, look at different goodness of fit measures, and then at the end, as a conclusion, you are asked to make a statement about the quality of the 3 predictive models you wrote and compare their performances. So you will basically be utilizing everything that you've learned in this lab and last week's labs. So if you need to talk to me in another Zoom meeting, email me right now. Otherwise, I'm going to stop sharing my screen and pass the host back to Dr. Cleveland. Sorry that I went over time again. Take care, everyone. Be safe. If you need to meet, send me an email. And that's it from me.
All right, everybody. Well, good day, and thank you very much. I hope you enjoyed archery and shooting, and just remember the old guy that occasionally hits stuff is more valuable than the drunk young guy that hits things but can't hit the same place twice. So have a good day, and we'll see you Thursday. Bye-bye.
Bye.
Be safe.